To show the algebra tile representation for 3x squared minus 7x minus 6, we want to arrange the 3x squareds together. Okay, and then we're going to have to arrange the 7x's, negative 7x's, and the minus 6. So we have a sum of negative 7x, so we know that's made up of two parts of these diagonals, and we have the negative 6 here. So what we want to do then is we need to figure out the split of the negative 7. So we get negative 18. So negative 18 products that add to negative 7 are going to be negative 9 and positive 2. So we need 9 x's or negative x's and 1 x's, positive x's. So to get negative 9, we probably don't want to put it along here because we'd have a big row of 9 here. That's a multiple of 1. But we would only have 3 groups in this direction, okay, because we have 3 groups of 3 this way. And it wouldn't make sense for the 2 to be along this edge because we can't fit 2 as a multiple of in here. So to show my negative 9x's, I'm going to do it along the edge with 3 x's. Okay, so I'm going to have negative 9 x's here. I'm going to put the positive 2 x's along this edge. Okay, and then the negative 6 ones should fit in here, and they do. So I have a 3 by 2 array, and that gives me my negative 6 x's. So then my length is going to be 3x, and it's going to be minus 1. And then along here, I'm going to have x plus 2, or x plus, minus 2, and x, that's going to be plus 2. And I have x minus 3 here. Okay, and that's going to give us the negative 3x squared here, or sorry, the positive 3x squared here, the negative 9x is here, the positive 2x is here. And again, I'll show that. This one's a little bit harder to see, so I'm going to show that in our regular simplified area model. And we're going to have 2x here and negative 9x here. Okay, so there's our length and width. This is our factored form then. So we have x minus 3, 3x plus 2. And since we drew them in rectangles, we can write them in factored form. So if it's in a rectangular array, we know we have our length and width. Okay, so there it is. So here's factoring a difference of squares. We know that difference of squares factors into a conjugate pair. And we need a conjugate pair because when we factor this as x squared minus y squared, we know that these two areas in here and here, they must cancel out. They must undo each other. To do that, we need a symmetrical length along here and here, but symmetrical and opposite. So to get that, we know that we have to have x times x, gives us x squared. If we have minus here, plus here, we have the positive xy and the negative xy that cancel out. And so factoring then becomes our conjugate pairs. Now, if you recognize that, it's just easy. We don't really need to draw a picture for every one of them, but again, it's important to understand why we're missing the middle term. And we're missing the middle term because they cancel out. The only way to make them cancel out is have opposite symmetry here, minus y and plus y. For this one here, we're going to have, again, a difference of squares. So we're going to take the square root plus the square root and the square root minus the square root. Again, here we don't have a perfect square here, and we don't have a, so this would not be able to, we would not be able to write this as a difference of squares. However, we always have to remember, and we should have mentioned up here, we always factor the greatest common factor. So here there is a greatest common factor of 2, and then when we factor that out, we end up with 4a squared. Well, that is a perfect square. B squared c squared is also a perfect square. Now we can use our conjugate pairing. So we're going to end up with 2a minus bc, 2a plus bc. Okay, there's our factored form. Why can we not factor x squared plus y into x plus y, x plus y? Well, if I first of all try to draw this out, okay, well, I have x squared, I have y squared. Well, these have to somehow cancel out. Well, if these were to cancel, they have to be opposite pairing. And when we have plus plus, well, that doesn't give us opposite. In fact, if we have plus y squared, that means that it is either negative and negative. Well, that's not opposite. Or positive and positive. Again, that's not opposite. So two squares never make a square. We could also look at it from the other perspective. Let's say we start with this. Well, this means it's a square. Okay. Well, we have x plus y, x plus y. This has to be a square, which means then we end up with x squared plus y squared, but now we have these extra pieces here which exist. Okay, before over here they don't exist. Okay, over here we don't have any extra terms here, so they could, only way that they could exist if they were opposites. Again, we've established that they can't be opposites, so we don't end up with a square shape. Square plus square is never square shape, whereas if we have a square here, we're going to end up with these parts going to be, we're going to end up with pieces here and here. And that argument works either for the plus plus or the minus minus.